Assalamualaikum and hello to everyone. So this is part 2 for our previously question. Okay, so we will continue with state 4 of our question. So state 4 here, the pressure is at the intermediate pressure. Okay, so for pressure 4, it is 3 megapascal. Okay, 3 megapascal or 3000 kilopascal. Okay, since this is ideal cycle, so the entropy at state 4, or we can write here S4S, is equals to the entropy at state 3, which in the last video we have found to be 6.7266. Okay, so using this entropy, okay, we will look at table A5. Okay, at 3000 kilopascal, and we will compare the entropy with the value for Sg. Okay, and looking at the table, the value is greater than Sg, so the phase here will be superheated. Okay, so the steam exiting the turbine, the high pressure turbine, is still in the superheated form. So when superheated, we have to open table A6, 3 megapascal, and using the value 6.7266 kilojoules per kg Kelvin, we will interpolate. Okay, we have to interpolate. So when we have to interpolate, looking at the table here, alright, we have to locate. Okay, we have to locate where 6.7266 is. Okay, so we have 6.7450, and then we have 6.5412. Okay, so we want to interpolate for H4S. Okay, so for the upper value is 3116.1, and the lower value is 2994.3. Okay, so doing our interpolation, so we can get the enthalpy at state 4, the ideal enthalpy at state 4 is 3105.1 kilojoules per kg. Okay, so then we proceed with state 5. State 5. Okay, state 5 here. The pressure is the same as pressure 4, so 3 megapascal, 3000 kilopascal. The temperature, the reheating, after reheating, the temperature will be 500. Okay, so same table A5, 3000 kilopascal. Comparing the temperature at state 5 with the saturation temperature, it is still greater, so the phase is still in the superheated form. Okay, so using table A6 at 3 megapascal, 500 degrees Celsius. Okay, if we can read directly, we will read directly. If not, we have to interpolate. So here we can read for H5. Okay, so H5 here is 3457.2 kilojoules per kg. And as well, we have to read for the entropy. Okay, so 7.2359 kilojoules per kg Kelvin. Okay, so next we have to, let me add another slide here. Okay, next we have to look at state 6. Okay, so state 6 here. So state 6 will be the same pressure as state 1 just now. So pressure 6 is 20 kilopascal. Okay, ideal process at the low pressure turbine. So ideal S6 here, S equals to S5. So 7.2359 kilojoule per kg. Okay, then as usual, we look at table A5 at 20 kilopascal. We compare S6S with Sg. Okay, so it is less than Sg, and then we look at Sf, so it's greater than Sf, so it's in between, so the phase is a mixture. Okay, so when it's a mixture, we have to find the quality. Okay, so using S6S equals to Sf plus X Sfg, we will find the quality. So X, looking at the table to read for value Sf and Sfg. So S6S here is 7.2359. SFG here is SF here is 0.8320. SFG here is 7.0752. Okay, so this will give us a quality of 0.905. So then we can use the equation of mixture, okay, for specific enthalpy. So we have here 251.42 plus 0.9505, and then HFG is 2357.5. Okay, this will give us a ideal specific enthalpy at stage 6 of 2384.96, okay, kilojoules per kg. So once all the properties are calculated, so we can proceed with drawing the schematic diagram, drawing the TS diagram. Okay, so all the phases are known, so we can draw the TS diagram. So the TS diagram, for a ideal reheat Rankine, we have to play around. Okay, because we have to make sure the phases are correct, so we have to play around with it. Okay, so we have the saturation line. Now we know that state 3 is a superheated. Okay, so this is state 3 here. We have to play around a bit. And then we know that state 4 also is a superheated, so we can plot it there here first. We know that state 5 and state 3 here is the same pressure, so state 5 will be somewhere here. Okay, and then state 6 will be mixture, so we can plot it straight under the state 5 because isentropic, so state 6 will be here. Okay, once we have the phases correctly, then we can draw the line. So state 4 and 5 is connected by the same pressure line. Okay, so here. Okay, and then we have state 3, the pressure line. Okay, we can extend it a bit here. Okay, doesn't matter. And then for state 6, okay, finish the constant pressure line. Okay, for state 1, saturated liquid. State 2, isentropic process to the highest pressure. Okay, so this is 8 megapascal, 3 megapascal, and 20 kilopascal. Okay, so once we have all the states, we can just connect the lines. Isentropic process, and then we can draw the line here and also the isentropic process here. Okay, so this is our TS diagram. We have to play around a bit to make sure that all the phases are correctly in their respective states. Okay, and then we can go for step 4, which is to substitute and solve for the question. Okay, so for workout, okay, we can write the equation again. Okay, equals to H3 minus H4 plus which H5 minus H6. Okay, so this is, okay, referring back all the entropies, the specific enthalpies. Okay, 2084.96. Okay, here we will get, we can calculate it individually. So this one will get 294.4, and this one will get, so plus 1072.24. So this will give us 1336.64. Okay, it's around our answers. So next is to calculate the thermal efficiency. So for thermal efficiency, the equation we know that is the work net output over the Q in total. So we have to calculate it individually. Okay, so for work net first is the workout total which we have calculated previously minus the work in which we have also calculated previously. Okay, so 1366.64 minus with the work input which we have calculated previously. So work input just now was 8.12. Okay, 8.12. So this will give us the answer. Okay, have to calculate it again. Okay, so it gives us the answer 1358.52. Okay, and then for our Q in total we have to calculate it again. So H3 minus H2S, okay, plus with H5 minus H4S. Okay, so this one will give us the values. Okay, the value of for H3 3399.5 minus H2 259.54. Okay, so for H5 here is 3457.2. H4S here is 3105.1. Okay, so this will give us individually 3139.96 plus with this one will give us 352.1. So total is 3492.06 kilojoules per kg. So substituting the values in the thermal efficiency equation here, okay, so we can get 1366.64 for work net. Sorry, let's work out. So work net just now was 1358, 52 over 3492.06. So this will give us the answer we get 0.389, okay, which we can say is 0.39. So we multiply it with 100, so we can get 39%. Okay, so the cycle efficiency is 39%. So let's check back at the answers. Okay, so we have the work output 1366, okay, and also the cycle efficiency is 39%. So this is the solution for this question. So if you have any questions, please do not hesitate to ask me. Okay, if there are any misunderstanding regarding the solution, you can come and talk to me. Okay, so thank you for your attention and have a good day.